Hi all, so we're going to spend the next 2 weeks talking about proofs with induction, which you maybe will recall from pre-calculus all the way back in the day. And it's in chapter 10, and we're going to break it up into 4 problem sets over the next 2 weeks. And those are all going to be based on what type of problem they are, and then you'll have some time to just practice some general types. Now, this first day we're going to start with the ones that are going to be most familiar based on your memory from pre-calc, and that's where we're talking about summations or series. So things where you're adding up a bunch of terms, like what we see in number 1 and number 2 here. Now, what you would hopefully remember from induction before, if you want to pause here, take some notes. If you haven't gotten yourself ready for notes, please do that now. We've got our steps of induction here, and the first one is what we call the base case, and that's where we want to prove true for n equals 1 or the least term. So if it says are natural numbers that are greater than 2, that are greater than 3, something like that will occasionally happen. You just want to prove true for the smallest number, which in most cases will be n equals 1. Then what we do is we say, all right, well then we know the statement is true for some natural number. When we say some in this case, we mean at least one number this is true for. Now we'll show that means that it's true for k plus 1. So if it's true for k, we can prove that it's true for k plus 1, the next consecutive number. We're going to prove that using an algebraic proof, and then we have the conclusion that since the statement is true for n equals 1 and all consecutive numbers, it must be true for all natural numbers, because that's how we define natural numbers. 1, then 2, then 3, then 4, etc., all on up. Now, let's actually look at a proof. So if n is a natural number, then 1 plus 3 plus the odd numbers, 2n minus 1 in this case, equals n squared. So what we're always going to do is start with step number 1, our base case, which in this case is 1. So we're going to say that n equals 1. Then using the formula here, we get 2, that should be a parenthesis, 2 times 1 minus 1 is equal to 1 squared, and that's a question mark. We want to know if that's true. Well, then 2 times 1 minus 1 is equal to 2 minus 1, which is 1, which is indeed equal to 1 squared. So now we know that this is true. Now, because of time and space, I'm not going to write out the whole entirety of step 2, but the conclusion of step 2 is that we know, so if you have Mr. Stick, you recognize this, we know that 1 plus 3 plus 2k minus 1. So we know that this is true for some k in the natural numbers. And then what we want is that 1 plus 3 plus 2 times k plus 1. So show that it's true for k plus 1. So again, we know it's true for some k, and we want to show this. This is what we want to end up with at the end of our algebraic proof. So what I will generally do with our summations is I will say, now we know that 1 plus 3 plus 2k minus 1 equals k squared is an equation. So that means that we can treat it like any other equation, and we can add, subtract, do anything we want to both sides. So what I'm going to do here is add the k plus 1 term. So then what I have is I now have my summation is what I want it to be, right? It's the series all added up. So now the left side of my equation is what I want it to be. But it's an equation, so I have to add the same thing to both sides. And because we started with something we know is true, we can do that with our equation. And so we get 1 plus 3 plus, and I'm going to just jump to k plus 1 minus 1 So we know that this is equal to k squared plus 2k plus 1 minus 1. Now what we want is this part here to equal k plus 1 squared. So that's what we want it to be. And we can do our algebra to show, well, this is k squared plus 2k plus 2 minus 1, which is equal to k squared plus 2k plus 1, which is indeed k plus 1 squared, which is what we wanted here. And our sum is what we wanted over there. Oh, I keep adding a little negative sign in here. That's all right. Got an eraser. So now that I've shown that it's true for 1, and now I can show it's true for consecutive numbers, this is now where we can state our conclusion. Please write out your conclusion as a full sentence. Same with your assumption. Don't really have enough space here, unfortunately. That was poor planning on my part. So we can say that since 1 plus 3 plus all the way out to 2n minus 1 is equal to n squared when n is equal to 1, and all consecutive numbers, then it is true for all natural numbers. Again, hopefully this feels a bit familiar. Let's look at one more example. What we're going to do here is we're going to see some with factorial, so it's nice to see that really quick. Again, as always, start with that first term. Say that n is equal to 1. Equal to 1. So then the question becomes, is 1 over 2 factorial equal to 1 over, equal to 1 minus 1 over 1 plus 1 factorial? We don't know, but we know that this is 1 over 2. And this would be 1 minus 1 over 2, which are in fact equal. So again, we will say, all right, we know it's true for some k. We want to show it's true for k equals 1. So I'm going to clear this so I have space in my notes. And now when I'm going to jump to the algebraic step here, and I will say, so we know 1 over 2 factorial plus all the way out to k over k plus 1 factorial equals 1 minus 1 over k plus 1 factorial. We know that this is true for some k. Now, again, just like last time, I'm going to add the next term in the series, because I can do that to both sides. So k plus 1 over k plus 2. Add it to both sides. So now the summation side is exactly what we want, and this is what you're going to be using for a lot of the problem sets. So now you have the k plus 1 side of the summation, and what we want on the other side, we currently have 1 minus 1 over k plus 1 factorial plus k plus 1 over k plus 2 factorial. And what we want on this side is it to look like this, except for n is equal to k plus 1. So we want 1 minus 1 over k plus 2. So we want 1 minus 1 over k plus 2 factorial. So because I know this, I'm going to leave this 1 here, since that's going to directly correspond, and I'm going to try to combine these two fractions. Now if I have k plus 1 factorial in the denominator and k plus 2 factorial in the denominator, and I want a k plus 2 factorial denominator, I'm going to multiply this fraction by k plus 2. Because if I've got a factorial, I just need that next term since they're consecutive. So that gives me 1 minus k plus 2 over k plus 2 factorial plus k plus 1 over k plus 2 factorial. Now we have common denominator, so we can combine like terms. One really important thing here is that we've got this subtraction here. We want to keep subtraction there. So I'm going to write this as, if you want to do it like this, just to help you understand the logic here, because we want to keep that subtraction. So then this would be minus with the double negative. If we put it in bounds like that, and that gives us 1 minus k plus 2 minus k minus 1, because we're subtracting the whole numerator, over k plus 2 factorial. We've got our like terms canceling out, and these do simplify, so we end up with 1 minus 1 over k plus 2 factorial. So that's our entirety of step 3 with the factorial. We can then state our conclusion that since this is true for n equals 1 and all consecutive numbers, it is true for all natural numbers. All right, so if you have questions on any of the summation induction steps or any of the induction questions in general, please be in touch and I will be happy to walk you through any of those problems, including the presentation. Have a wonderful day.